Hey Stats class, I'm going to show you how you can use a spreadsheet to help with these confidence intervals in 7.3. So we are trying to find a confidence interval. We're given some summary statistics and they give us the confidence level that we need. So first of all, the degrees of freedom here, the nice thing about this is very similar to the degrees of freedom we did with the t intervals. So it's one less than your sample size. So our sample size is 26. So our degrees of freedom is 25. All right, now these left and right chi-square values. So visually, the chi-square distribution starts at 0, and it's a right skew distribution, so it's not symmetric. So it can't have like a 0 in the middle and plus and minus values anymore. So when we have a particular confidence level, what happens is that means that there's 80% trapped in the middle of this right skewed curve now, and that leaves 20% left over. But because there's two tails, that means half of the 20% is in the upper tail and the other half is down here in the lower tail. Now one thing about the chi-square distribution, it always starts at 0. So that's the lowest number in the chi-square distribution. The numbers here, this number is unknown. We don't know what it is. Some value, some chi-square value. But we don't know what it is. But the area to the left of it is 10%. And for this one right here, the area to the right of it is 10%. So this is chi-square right, this is chi-square left. The area to the right of that one is 10%, the area to the left of this one's 10%. And we can use a feature in the spreadsheet. And there's two of them. I'm going to just type in equals and start typing CHI for chi. And the two of them we want, this one calculates the inverse of the right-tailed chi-square. And then we also have chi-square dot INV. Calculates the inverse of the left-tailed chi-square distribution. So actually, I'm going to use chi-square dot INV and chi-square dot INV RT. Calculates the inverse of the right-tailed chi-square. So I actually think these are the same. But I'm going to use the .inv for left and .inv.rt for right. So I'm going to click this so you can see it. The probability, again, that's the area. Area is probability in this case. So that's what I was saying before. Because it's 80%, there's 10% below in the left tail and 10% up in the right tail. So this is the left tail. So it's chi-squared 0.1. The degrees of freedom is 25. And so there is my lower number, 16.47. Oh, sorry, it wants 3 decimal places. Let me go back here. All right, and add more decimal places. So 16.473. Make sure you're rounding to where they tell you to round. All right, now the other one, right underneath it, I can do equals and start typing CHI again. And I want .inv.rt, the right tail chi-square. So in the right tail, the area is also 10%. And we also have 25 degrees of freedom here. So now this is 34.382 to 3 places. So that's the right tail chi-square distribution. Now, the confidence interval uses these, but those are not the left and right numbers. So don't just put this number here and this number here. So what we have to do here, the formula is we're going to start off with the square root of our degrees of freedom. We're going to multiply by this S value right here, squared. And then we're going to divide by these two numbers. The first one we're actually going to divide by the chi-square right. That's going to be the first number, even though it says right, and that's the one on the left. Chi-square right is a bigger number, And when you divide, both of these are going to have the same numerator. They're both going to have the degrees of freedom times s squared. It's just the denominators are changing from chi-squared right to chi-squared left. And because this is a bigger denominator, when you divide by a bigger number, you get a smaller fraction. Like, for instance, 1/5 versus 1/3. Right? This is a bigger number. 1/5 is 0.2. 1/3, smaller number on the bottom, but 1/3 is 0.3. 0.3333. So 0.2 is less than 0.3. So dividing by a bigger number makes a smaller overall fraction. So that's why we are dividing by the right chi-square for the left number in the interval, the lower number. But it's this number squared times the degrees of freedom divided by these two numbers. So I'm going to write, again, I like to do labels. This is lower, this is upper. I'm going to call this chi-square L, call this chi-square R. My lower number is equal to SQRT square root, open the parentheses, the degrees of freedom, one less than n, so 25 times s squared, so 0.29 squared. Shift 6 for the power of 2, and then that is divided by, the first time it's going to be chi-square R. So click this number, close that parentheses. All right, give yourself some more decimal places. It was giving me 0 there. So I added some decimal places. All right, equals the exact same thing. SQRT square root, open a parentheses, degrees of freedom, 25 times .29 squared, but this time, instead of dividing by chi-squared R, I'm going to divide by chi-squared L. And again, let me give it some more decimal places. You might see it look like that when you're doing it. Alright, rounding these to 2 places it says, so that's going to be 0.25, and that one's going to be 0.36. Alright, and that is how we do a confidence interval for standard deviation. You got to remember, standard deviations are, their distribution is not, they don't target their mean. They're not symmetric. They're not. It's a biased estimator. It tends to overestimate because of the right skewed distribution. So because of that, we have a completely different procedure. So it's important that you kind of follow along and you do these calculations.